this is a section about continuity. So basically, what is continuity? Without looking at the definition, so let's say a function is continuous from point A to point B. So we have a point at point A, and then we have a point anywhere in point B. A function is continuous between point A and point B, simply speaking, without any technical language. That means you can sketch a curve between point A and B without picking up your pencil. Okay, so from point A to point B, you can just connect them, draw any curve you like without picking up your pencil. So how about using some technical language? Let's read the definition. A function f is continuous at a number a if the limit of f when x approaches to a is equals to f of a. There are three required conditions. Number one is f of a is defined. Notice this is a function evaluation. It is not a limit. F of a is defined, so that means there is a solid point. When x is equals to a, y is equals to f of a. This is a solid point. And then number two, the limit exists. I didn't say the left or right. I say the limit exists that includes the left and the right. So we have a solid point. We have a left curve connecting that point. We have a right curve connecting that point. That means you can just pass through that point. So let's bring 1, 2, and 3 into one graph. So we have a y-axis, and then we have an x-axis. So this is my x, and then this is my y. F of a is defined. So I have a solid point right here. This point is when x is equals to a, y is equal to f of a. It's a solid point. Okay, it is not an open circle, not a vertical asymptote. And then the left limit exists, the right limit exists. That means on the left-hand side of the point, we have a curve going toward that point, and then the curve will go through that point. So we have a left limit. So let's say this is a left limit. The left curve approaching to that point, and then will pass through that point. And then the right limit, we have another curve approaching to that point, and then pass through that point. So overall, we can draw a curve. So this curve will just left limit, pass through that point, and then right limit. So that means the function is continuous when x is equal to a. All right. So again, we have a point at x equals to a. We have a left limit approaching to a, and then pass through that point, and then we have a right limit approaches to a and touching a. So basically, after you are done, you can draw one curve without picking up your pencil. So f is continuous at x equals to a. So these three conditions must be satisfied in order to say that the function is continuous at x equals to a. What if they are not satisfied? If they are not satisfied, then we say, okay, so let me change color. If they are not satisfied, so if 1, 2, 3 are not satisfied, let's say one of them is fail, not satisfied, then f is not continuous, or you can use the word discontinuous at x equals to a. This is a very important concept in limit. All right, you need a solid point. Okay, the point must be solid, just like driving. You have a point, you must be able to drive through that point. All right, and then you approach to that point from the left. You are driving from the left, past. You can stop at that point, no question at all. And then another car can drive to that point from the right side and is able to pass through that point. That means the road is clear, right? So you can drive here, right here. You can drive here, drive through that point without a single problem. So that is continuity. So let's take a look at a problem. I have a picture. I want you to point out which number is f discontinuous. So looking at that graph, what do you see? First, I see two curves broken down at x equals to 3. I see there are empty circle or open circle at x equals to 1, 3, and 5. All right. So where are the discontinuity? So there are 3 discontinuity. So 3 discontinuity. we have x equals to 1, x equals to 3, x equals to 5. There are 3 discontinuity. So let's check the first one. Number 1, why is number 1 a discontinuity? Because f of 1 is undefined. It is an open circle. When x equals to 1, the function is undefined. When you plug in 1 into the function, I don't care what the function is, you are not going to get a y value. Alright? How about number 3? Number 3, you can argue with me and say, hey, no. Look, f of 3 is defined. That means there is a solid point, right? I agree with you. There is a solid point. However, x approaches to 3 from the left. What do you get? You get a negative y, right? So it's not equal to x approaches to 3 from the right. So as x approaches to 3 from the right, you are right here, right? You get a positive y. As x approaches to 3 from the left, you get a negative y. So they are not the same. They are not going. As x approaches to 3 from either side, they are not going to be connected. So when x is equals to positive 3, the function is not continuous. To be more specific, you can do this. The limit as x approaches to 3 from the left of whatever the function is not equal to the limit as x approaches to 3 from the right of that function. They are not connected. Number 1, the first condition is a solid point. Number 2 is you have to make sure that they are connected. Number 3 is you want to make sure the left limit, the right limit, and the point, they are connected at the same point. So that is another way to describe conditions 1, 2, and 3. How about number 5? Number 5, you have something similar. F of 5 is defined. This point is f of 5. I should not say f of 5, so let me erase that quickly. So this point is when x is equals to 5, y is equals to f of 5, whatever the value is. There is a solid point right there. However, the left limit and the right limit and the solid point, they are not connecting, right? The left limit and the right limit, they are approaching to this point. Is a y value that is less than that. So let's say this is a 4. So this point will be 5, 4. And then obviously, this y value is not 4, right? So as x approaches to 5 from the left, from the right, the limit is not going to be equal to 4. Okay, so that means number 3 is not satisfied. So for f of 5, we have 5, f of 5. This is a solid point. And then we have limit as x approaches to 3 from 5, left side, is equal to the limit as x approaches to 5 from the right. Yes, they are equal. So number 1 is satisfied. Number 2 is satisfied. However, the limit as x approaches to 5 from either side is not equal to f of 5. They are saying that, all right, the point is solid, the left limit and the right limit, they are connected at a point. However, they are connected at a point. It is not the solid point, right? So we have a car coming in from the left, a car coming in from the right at this point. However, the solid point is right there. So this curve is not going to, you cannot just drive a car to pass through this road because this is open circle. These two roads, they don't join, they join at the same point, but at that point, it is not solid. So you still cannot pass through. So there is a discontinuity at x equals to 5. So how many types of discontinuities are there? There are 3 of them. I know there are 4 figures, but we have 2 for removable discontinuity. The first one is removable discontinuity. What is removable? We talked about that in the previous lesson. We have x squared minus x minus 2 divided by x minus 2. When x equals to 2, there is an open circle, right? There is an open circle. However, that is not a vertical asymptote. That means that when x is equals to 2, although this is my biggest enemy, this enemy can be eliminated by doing what? By doing some algebra. So this is x minus 2, x plus 1 divided by x minus 2. You get rid of them. That is just equals to x plus 1. How come we don't just graph x plus 1? Well, x minus 2 in the denominator is part of the function. You cannot just ignore it. But once you graph it, x cannot be equal to 2, right? It's part of the function. It's like a machine. There is a part. It is part of the machine. You cannot remove it. If you remove it, the machine is not going to work. Function works like a machine, right? So there is a discontinuity, then it is there, but it is removable. So we have an open circle. So that is the first type. So let's take a look at the piecewise function. So we have a function as x. We have a function, so that is the straight line. How come there is a solid point? They have a solid point when x is equals to 2 exactly. That point is at 1. So this point is 2 comma 1. However, this point is not on there. So when you drive from the left, from the right. Yes, you can approach to this open circle. However, this open circle is not solid. They put the solid circle in somewhere else. So what does that mean? That means you still cannot pass through that row because there is an open circle. So that is the first type of discontinuity. The second type, you will see the first two types a lot. The jump, you won't see that very often. The second type is infinite discontinuity. Infinite discontinuity means, here, look at this piecewise function. Look at the denominator, x squared. Can you do algebra to remove the x squared? The answer is no. When x is equals to 0, we have a trouble. And this trouble cannot be eliminated, so therefore we have a vertical asymptote. And this is called an infinite discontinuity because as x approaches to x equals to 0 in either direction, well, the function is either go all the way up to positive infinity or go all the way down to negative infinity. This curve, it doesn't have to go this way. This curve, so imagine that this curve doesn't exist. You can have something like this. As x approaches to the function from the left, you have y approaches to positive infinity. X approaches to 0 from the left, y approaches to positive infinity. X approaches to 0 from the right, y approaches to negative infinity. This works, but that is not the case, right? All right, so we can just erase that really quick. So as x approaches to 0 from either direction, y approaches to positive infinity. But positive infinity is not a solid point. It will just go up forever, right? So that is not a solid point. Then it is still not continuous. So as you drive from the right, you will just go north forever. You will not be able to touch this piece at all. If you drive to x equals to 0 in this direction, there is no way to jump to the other row. Impossible. Because at x equals to 0, the function is discontinuous. It's not connected. The last one is a jump discontinuity. This is called a step function. All right, this one you won't see that very often. So this you don't need to worry about it. Jump discontinuity means, so you can clearly see that, so let's say we pick this piece. Let's say we pick this piece, x approaches to 1 from the left is not the same as x approaches to 1 from the right. So the left limit and the right limit, they are not equal. That means they are not joining at the same point. So the function is not continuous at that point. And in case you are wondering, how come they have a solid circle and then an open circle? Because a function has to be 1 to 1. 1 to 1 means when you check out the graph, it must pass the vertical line test. If you draw a vertical line test, the vertical line test can only intersect the function one time only. So that is a 1-to-1 function. For every x you have in that function, the x goes to 1 y value. So that's why is one open circle and one solid circle. So let's take a look at some exercise. So we have another graph. I want you to find the discontinuity. Also find the interval where the function is continuous. So let's find the discontinuities. You can see there are a few, right? So the discontinuity, we have x equals to, from left to right, we have -4, right? We have x equals to -2, and then we have x equals to 2, and x equals to 4. So at x equals to -4, what happened? So x equals to -4, we have the left limit not equal to the right limit. They are not the same, right? And f of -4 itself, oh no, not equal. Although they are equal, when x is equals to 4, we have undefined. Although the left limit and the right limit, they are connecting at the same point, at that connecting point, the function is undefined, so it is discontinuous. And then at x equals to -2, so x equals to -2, what happened? As x approaches to -2 from the left, we have a solid point is not equal to x approaches to -2 from the right. So they are not joining at the same point. So I don't even care about whether that is defined or not at x equals to -2. All right. And then at x equals to 2, what happened? X approaches to 2 from the left is not the same as x approaches to 2 from the right. They are not connected at the same point. I don't care the function is defined or not at x equals to 2. They are not connected at the same point. It's like two different rows. You can pass through, right? And then at x equals to 4, what happened? So as x approaches to 4 from the left, we have the limit as x approaches to 4 from the left of whatever that function is, y approaches to -infinity. It will just go down forever. And then that is not equal to the limit as x approaches to 4 from the right. Forgot a plus, because as x approaches to 4 from the right, we have a solid point. I don't know what this is, I can't tell, but that is a solid point. So just say they are not equal. So that is the reason. And then the function is continuous in where? So here is how we describe the continuity. So let me change color first. So we have a function from -infinity to +infinity. And then you grab a hole puncher. You are trying to punch hole on a piece of paper, or you are trying to punch some hole on a roll. So at x equals to -4, you punch a hole. X equals to -2, x equals to 2, and x equals to 4. You're trying to punch one hole in here, one in here, one in here, one in here. Hole puncher, right? You punch holes on paper. So you punch 4 holes right here. So the function is continuous in where? Is continuous in everywhere else except these 4 holes. So how many pieces do we have? 1, 2, 3, 4, 5. All right. So the first piece is from -infinity to -4, right? I am using interval. This is not a order pair. And then from -4 to -2, I am going to use a solid circle. I am going to use a square bracket. This is called interval notation. I use a square bracket is because at x equals to -2 on the left side, we have a solid point. And then from -2 is not a square bracket anymore, because this, just look at my arrow. This is not a solid point. And then to 2, right? 2 is an open circle. So open circle, so we use a parenthesis. And then the 2 on the right side is a square bracket, because this is a solid point. And then all the way to 4, we use open parenthesis, because that goes down all the way. And then finally from 4, so let me erase the orange dot to make sure that this is a solid circle. And then from past the 4 all the way to past infinity. So there are 5 intervals, 1, 2, 3, 4, 5. To take care of the square bracket means a solid circle. You have to look at the graph. All right, so that is how you solve a graph problem. So in the next part, I will give you more example about continuity, discontinuity, and removable discontinuity. I will see you there.